Okay, good morning, everyone. Can you see the whiteboard?
Yes.
Okay. Okay, so let's continue and let's see some other examples of first order systems. As I mentioned the last time, an isothermal CSTR with a first order reaction is a first order system. Just in this case, if the CSTR is not isothermal or the reaction is not first order, is not the first order system. So let's consider the classical situation. We have a CSTR, VI dot is the inlet volume flow rate, CAI is the inlet reactant concentration. The reaction is elementary, A that gives B. First order, the temperature is constant, so the kinetic constant is constant. And we have also constant level, so which means that the overall volume is constant, which means that the inlet flow rate is constant. As we will see, the sole disturbance that we will consider is eventually a disturbance in the inlet concentration, but we will see this in one moment. So, molar balance for the reactant as usual. Let me simplify a little bit this expression here. V over VI dot is what we call the characteristic time. For now, let's call this characteristic time TR. And so let's rewrite the mole balance in terms of TR as usual. Now, to realize that this is a linear differential equation, we can rewrite this in the canonical form to get an expression like this. So I just transported CA and CA, these two terms, on this side. So now is this equation linear or non-linear?
Linear.
Linear, because K is constant, temperature is constant, TR is constant because V and VI dot are constant. And so it's linear. So now we need just to rewrite this in the deviation variable form. So let's write the same equation around the original steady state, and then let's subtract term by term to get basically the differential equation, which is linear and is written in the deviation variable form. So very easy. Now, next step will be find a transfer function for this system and recognize that this is a first order system. But we already recognize this. First order differential equation, first order system. So we can already recognize this. So let's transform with Laplace and we get TR as Y capitalized, CA capitalized, plus 1 plus KTR CA capitalized equal to CAI capitalized. So if I collect CA, I get TR as plus 1 plus KTR equal to CAI capitalized. And so the transfer function, which by definition is CA capitalized over CAI capitalized, is 1 divided TR as plus 1 plus KTR. And so this is clearly the transfer function of a first order system. Now, guys, is this transfer function written in the standard form? Let's just compare this with the standard form of a first order transfer function. Is this written in the standard form?
No.
No, because this coefficient is not 1. Is 1 plus KTR. Make sense? So I have to make sure I transform this into 1. So let me collect this out. 1 plus KTR, which multiplies TR divided 1 plus KTR S plus 1. And so what we get is finally, so now question for you, who is a KP and who is tau P? Who is KP? Please wake up. Who is KP? Okay, is 1 over 1 plus KTR. Who is tau P? Okay.
TR over 1 plus KTR?
Yes. TR divided 1 plus KTR. KP and tau P. So this is a first order system. So now the question is, what if there is a step change in the inlet reactant concentration whose amplitude is A? We have a step of amplitude A, a step change of amplitude A in the inlet reactant concentration CAI. What happens to the outlet if the inlet reactant concentration increases, by a step of amplitude A? What is the effect on the output in short times and over long times? Okay, as usual, the response in the Laplace domain is the transfer function times the Laplace transform of the disturbance is a step of amplitude A in the inlet reactant concentration, and so the Laplace transform will be A over S. Does this make sense for everyone?
Yes.
Yes. Okay. So, does this respond our question? No. This is the response in the Laplace domain. We need to anti-transform and basically get the response in the time domain. So this is a very elementary situation. You don't even need to use Heaviside. So it's simply, if you look into your tables, I think you can find very easily the anti-transform of this expression, which is the following. Is an expression like this. Okay, let me understand a little bit better. So there is a step change of amplitude A in the inlet reactant concentration. How the outlet concentration, which is also the concentration in the reactor, because it's perfectly mixed, respond. So when time is 0, where the exponential goes? Okay, the exponential goes to 1. 1 minus 1 is 0. So at the time 0, the response is 0. If time goes to infinity, the exponential term will go to 0. And so basically, the asymptotic response of the system will be A divided 1 plus KTR. And so basically, the system will respond in this way. There is an instantaneous step change in the inlet reactant concentration at the time equal to 0, and in a sluggish way, the system responds. And so the concentration also moves, the final asymptotic concentration moves to a new steady state, unless you take control action, as we will see soon. So what happens? What happens if the kinetic constant increases? If the kinetic constant increases, just remember that tau P is TR over 1 plus KTR. If the kinetic constant K increases, what happens to tau P?
It decreases.
Decreases. And so the response will be faster or slower. So if tau P decreases, the response will be faster, And so you will have, the system will reach a new steady state much faster. So how can you interpret this from the physical point of view? If the kinetic constant increases, the reaction becomes faster. The reaction becomes faster, and so the extra reactant that I have fed to the system is consumed faster. And so the response of the system will be something like, you know, the asymptotic response will be much lower. Does this make sense for everyone?
Yes.
Simple. Every time we have a mathematical meaning and a physical meaning. Mathematical meaning means tau P, if K increases, tau P decreases. So the response is faster. Physical meaning, if K increases, the reaction becomes faster. So the extra reactant that I have fed at time zero is consumed faster. That's why we have this kind of response. So everything really makes sense.
Dr. Galizia,
Yes,
I'm still a little confused. What is TR again?
TR is a
Yeah.
characteristic time, and I'm glad that you brought this to the attention, Alexei. Let me just erase and say a few words about it. So TR was basically V over VI dot, volume over inlet flow rate. Make sense?
Yes.
So is, let's say, a characteristic time. Now, tau P is TR over 1 plus KTR. So basically, TR and tau P, they are not the same. TR is the residence time. So is the average time that every droplet of liquid basically spans into the system. Make sense?
Yes.
Tau P is not the residence time in this case. When tau P is the residence time? If we want tau P to be equal to TR, we need to have K equal to 0. If there is no reaction, if this is simply a mixer, TR and tau P will be the same. Otherwise, if the system is reacting, tau P, the constant, the time constant tau P, is not equal to the TR constant. So the residence time is not normally equal to. Does this make sense?
Yes.
Just now, just to complete, let's consider a relatively more complicated situation. Systems with the 2 inputs and 1 output. With 2 inputs and 1 output. So I feed a liquid with the volumetric flow rate VI dot and at the temperature Ti. Then there is a coil. I feed vapor to the coil and basically I warm this liquid up. So it is a stirred tank heater. And then I remove the liquid heated up at a temperature T. Make sense?
Yes.
So let's consider the level is constant. Level is constant. So first question, let's find a transfer function or the transfer functions for this system. So level is constant. Let's write, it's a pure fluid. Level is constant. We don't really need to write the mass balance. We can write directly the energy balance. And so basically we have V rho Cp, derivative of temperature with respect to time. V is the hold-up volume, rho is the density, Cp is the specific heat of this liquid, equal to Vi dot rho Cp Ti minus T plus UA Tbu minus T, which corresponds to Q point, corresponds to the heat that this vapor is releasing to this liquid to warm it up. U is the overall thermal exchange coefficient. A is the area of this coil, the area of thermal exchange. Make sense for everyone?
Yes.
Let's rewrite this in a more understandable way. So, is this equation linear or non-linear? Sorry? It's linear. It's linear, this is a number, this is a coefficient, this is a coefficient, this is a coefficient. So we don't need to linearize. So let me rewrite this by dividing everything by V rho Cp. Okay, so Tr is clearly V over Vi dot, as usual. Now, who is the input here, guys? How many inputs do we have? How many inputs do we have?
2.
2. Who are the inputs here?
Ti and Vi.
That's right. Input, input, and the output is T. Just remember that we saw this a few classes ago. So here, when you have multiple inputs at the right side, you have the sum of the inputs, everyone multiplied by its own constant. Now, let me call this K, UA divided V rho Cp. Let me call this K. And so now this is to manage this equation more easily, to not bring with us too many constants. So it's linear. Now we have to write this in the deviation variable form. So just subtract the same equation written in the original steady state, and basically you get, now at this point you are expert, based also on the output of the second homework, I will just report the deviated form of this expression. So now next step is to transform with the Laplace. I want to do something more. I can call this A to make this expression even shorter. So let me transform with Laplace S times the Laplace transform of the temperature plus A, the Laplace transform of the temperature, equal to 1 over Tr, the Laplace transform of Ti, plus K, the Laplace transform of Tv. Make sense?
Yes.
Okay, so now just a little bit of algebra. Let me divide by S plus A, and so we have that temperature in the Laplace domain is 1 over Tr divided S plus A times the Laplace transform of the inlet temperature plus K divided S plus A, the Laplace transform of the vapor temperature. So how many transfer functions do I have?
2.
Two. One that relates the output T to the inlet temperature, and one that relates the output to the vapor temperature. So if we have n inputs, we have n transfer function, each one relating the output to the specific input. So just guys, make sure you study day by day. Let's consider the block diagram. The block diagram will be this. Transfer function number 1, 1 over TR divided S plus A. Transfer function number 2, K divided S plus A. The first transfer function relates the output to the first input. The second transfer function relates the output to the second input. Do you agree? Do you remember this?
Yes.
Yes.
Okay, simple. Please study day by day, because now we have to put everything together. So don't accumulate, because if you accumulate, it's difficult to follow. So now, why we did that? Here we go. What happens if we have a step change in Ti, in the inlet temperature? What happens to the output temperature? What happens to T if Ti undergoes a step change of magnitude A? Very easy. So, simply, the Laplace transform of T, so the response in the Laplace domain, will be the transfer function that relates T to Ti times the Laplace transform of the disturbance that hit Ti. Does this? I will go ahead. So the response in the temperature will be the transfer function that relates T to Ti, this one, times the Laplace transform of the disturbance, which is a step of amplitude A. So it will be A over S. Now, who is A? Just remember that before we assumed A equal to 1 plus KTR divided TR. So this will be the response in the time domain. So we need to rewrite this in a form that is easy to anti-transform. Guys, please, does this make sense?
Yes.
There is a microphone open, please. Okay. So let me write in a way that you can see. Okay, this should be better. So this is the response of T to this step change, but is in the Laplace domain. So we have to anti-transform this back to the time domain. This comes from this after adjusting a little bit the way this expression looks like, to make sure that we can anti-transform in an easy way. So if we anti-transform, and you can use the table directly, you get an expression that is very similar to the one we got before. I would say that is exactly the same, at least from a mathematical point of view. So if the inlet temperature undergoes a step, the dynamic response of the outlet temperature will be this. And so, basically, you will have a response like this. What is the asymptotic response of the time? When time goes to infinity, this exponential goes to 0. And so the exponential response will be A over 1 plus KTR, which is an expression similar to the one that we found before. Okay?
That makes sense.
Okay, so just to stress on this, if there is a disturbance in the inlet temperature, the response of the system will be simply the corresponding transfer function times the Laplace transform of the disturbance in the inlet temperature. If the question is, there is a disturbance in the vapor temperature, what is the response of the system temperature? Simply what you have to do is take the corresponding transfer function and multiply by the Laplace transform of the disturbance. If the two disturbances act simultaneously, simply you have to consider the summation, the sum of them. Make sense?
Mm-hmm. Yes.
So that's it. Does not really change anything. The approach is always the same, is very repetitive. And that's why here I didn't report all the calculations. It's always the same.
Can I ask a question?
Sure.
If we had, well, I guess, will we ever see a situation where a disturbance in one input results in a disturbance in the other input, like a related functions, I guess? No? Okay.
No, TV and the TI are not related to each other.
Okay, thank you.
They are independent inputs. So, make sense?
Yes.
Yeah. Simply, this comes from a vapor generator. This comes from another upstream side of the chemical plant. So they don't communicate. They don't know to each other. Okay. We will see, obviously, several other examples. But in the meantime, we need to do something else. And can you see my presentation now?
Yes.
Okay. So we have seen so far first order systems, but this does not really cover all the possible scenarios. We have other systems that are second order. Just remember that the first order systems are described by first order differential equations. Second order systems are systems described by second order differential equation. Just remember that regardless, the system is first, second, third order, or order n, whatever the order is, the system in our conception is linear, or it has been linearized. So please don't confuse the linearity with the order. A second order system, like the equation that you can see now on the screen and that I'm highlighting, that the second order equation is linear. So, linearity does not mean that the system is first order. Just remember the definition of a linear differential equation that I gave you a while ago, and that is reported in your slides. So a linear or linearized system like this, is second order when the output y and the input f are related by a linear second-order differential equation like this, where y is the output written in the deviation variable form, f is the input written in the deviation variable form, tau is a constant, and we will discuss this in a few seconds, xi is a constant, and kp is a constant. Make sense?
Yes.
Yes.
Okay. So first thing first, when you talk about something, give the definition. So tau is a time constant that we call natural period of oscillation, if you want, and it has exactly, as we will see, the same meaning that we saw for first order systems. The larger tau and the more sluggish the response of the system will be to any disturbance. And so basically it measures the time that the system takes to get adjusted to the disturbance. Kp is the steady state gain, and it has exactly the same meaning that I explained last time. So I won't explain that again. Xi is a new parameter that we didn't see in the first order system. And this is what we call damping factor. So this determines if the response of the system is oscillating or not oscillating. And indeed, get accustomed to this. So first order systems do not oscillate because they cannot exhibit complex poles. But second order systems or higher order systems, they might exhibit complex poles. So they might exhibit an oscillating response. And so Xi will tell you if the system oscillates or not. Now, let's go ahead. Let's find the transfer function, the general transfer function for a second order system. So follow my cursor. The starting point is the initial differential equation. Is this linear?
Yes.
Yes.
Yes. Is it written in the deviation variable form?
Yeah.
Yes. So we can transform directly. And so the transform is the one that I'm highlighting now. Tau square, s square, y, plus 2 xi tau, s y, plus y, equal to kp f, where this time y and f are the Laplace transformed. Definition of Laplace transform, definition of transfer function. Laplace transform of the output divided the Laplace transform of the input in the deviation variable form, so y capitalized over f capitalized, and so the transfer function is kp divided tau square s square plus 2 xi tau s plus 1. Are you surprised? Not at all. Second order system, second order transfer function. The coefficients of the denominator, tau square, 2 xi tau, and 1, are exactly the same coefficients of the terms in the original differential equation. Do you recognize them?
Yes.
So, as usual, really does not change anything. Simply now we have a second order transfer function. The order of the transfer function is the order of the denominator, remember. So now we have defined second order systems, we have defined the parameters, and now I know what you are thinking about. Please tell me an example of second order systems. Which unit in the chemical industry behaves like a second order system? So, to be honest with you guys, there are not that many systems that inherently behave like second order systems. Generally, they are systems that have resistance to, for example, motion, to fluid flow, to heat transfer. They are really rare. They are really quite rare. There is a situation where you can easily have second order systems. When you have a series of two first order systems, for example, a series of two isothermal CSTR with a first order reaction, that will be a second order system. And you probably can imagine why. Because when we have a series of systems, the overall transfer function is the product of the single transfer functions. So the product of two first order transfer functions is a second order transfer function. So if you have two first order systems in series, the overall system will be second order. Does this make sense?
Yes.
Okay. And third possibility, controlled processes. When you have a first order process, we will see this in a month or so, and you apply a controller, the order can increase. And so a first order controlled system can become second order system. So, but be aware that systems that are inherently second order are really uncommon. We have to classify now these systems because here, you know, the complexity is much bigger than first order. So a very convenient way to classify second order systems is based on the analysis of the poles. So let's take the transfer function. The poles are the roots of the denominator. So let's find the roots of the denominator, and E is basically the one that I'm highlighting now with my pointer. So a useful way to classify the poles is based on the delta. So if psi is larger than 1, the term underneath the square root is positive. And so you have two real and distinct poles. Does this make sense?
Yes.
So a second order whose poles are real and are distinct is called overdamped. Let's consider now a limiting case where Xi or Xi, you can call as you wish, is equal to 1. If Xi is equal to 1, what happens? We have two repeated poles. You know, the delta is equal to 0, and so you have two repeated poles, minus Xi over tau, and minus Xi over tau. So you have two repeated poles, real, but repeated. So this is critically damped. These systems are called critically damped. So third case, and probably most unfortunate, if Xi is less than 1, what happens to the square root?
There's a non-real portion.
Because you have the square root of a negative number. And so basically you have complex and conjugate poles. Here we are. For a first order system, we do not have this problem. When we have higher order systems, we do have this problem. You may have complex and conjugate poles. And so these systems will tend to oscillate, and they are called underdamped. So let's start with the overdamped systems. So again, let's consider the general transfer function for the second order systems, like the one that I'm showing you right now. So the way to identify if the system is over critically or underdamped is based on the analysis of Xi. So if Xi is larger than 1, the system is overdamped. And so you have two poles, both real, and they are distinct. So, question, do you expect any oscillating response for these systems if you disturb them?
No.
No, for sure they won't oscillate. So this is something that we can predict immediately. Well, first important implication: a series of two systems that are non-interacting, they will give rise to a second-order overdamped system. But to understand this, and before understanding this, we have to introduce the concept of interacting systems or non-interacting systems. So let's consider the system that you have here depicted in this figure. You have two first-order systems in series, whose transfer functions are Kp1 divided tau s1 plus 1, and Kp2 divided tau 2s plus 1. So the first basically influences the second, and the second influences the system because there is a recycle. A system like this is called interacting, because the first affects the second, obviously, because it comes first, but the second affects the first because there is a recycle. Does this make sense?
Yes.
So this is interacting. More in general, for this system to be non-interacting, what should you do?
Remove the feedback.
That's right. Remove the recycle. If you remove the recycle, the first will affect the second, but the second will not affect the first. And so in that case, if you remove the recycle, the system will be non-interacting. And so a series of n systems is defined non-interacting if the first n-1 systems influence the nth system, but not vice versa. Okay, make sense?
Yes.
Okay, so with this being said, with this definition being provided, we have now a statement that we have to demonstrate. A series of two non-interacting first-order systems gives rise to an overdamped second-order system. So consider the drawing that I have here, the two first-order systems in series. Is this interacting or non-interacting?
Non-interacting.
Non-interacting. There is no recycle. So the overall system, as you remember, is given, the overall transfer function is given by the product of the two transfer functions. And so the overall transfer function is Kp1, Kp2 divided tau 1s plus 1 times tau 2s plus 1. So let's develop this product at the denominator, and we get basically an expression that I'm highlighting now with my pointer. Is this expression in the middle? This is basically what you get from the product of the first two. So this really looks like a second-order system. However, what is the standard form of a second-order system? Kp divided tau square s square plus 2 psi tau s plus 1. And so guys, who is in this specific case tau square? Is the product of the two taus. If you compare this expression, the second, and this expression, the third, tau squared, the red factor is equal to tau 1, tau 2, the other red factor. 2 psi tau the green factor, is clearly equal to tau 1 plus tau 2. Does this make sense?
Yes.
So let's keep in mind this equality. Tau first, tau second is equal to tau squared. Tau first plus tau second is 2 xau tau. Okay, with this in mind, let's go ahead. Tau, the overall tau, will be, at this point, the square root of tau 1, tau 2, tau first, tau second. So if you consider the square root of the product of two numbers, how do you call that? You call that geometric average. So tau, the overall time constant, is the geometric average of the two time constants. Okay? Okay, this is easy. Now let's move to the second expression that we got. We got that tau first plus tau second is 2 psi tau. Now let's explicit psi from this expression, remembering that tau is the square root of tau 1, tau 2. And so we get, basically for psi, for the damping factor, an expression like this. Tau 1 plus tau 2 divided 2 times the square root of the product tau 1, tau 2. So guys, can you recognize that is the ratio between the arithmetic average and the geometric average?
Yes.
So if you remember from the high school or the calculus class, the ratio between the geometric average, between the arithmetic average and the geometric average is always larger than 1. And so Xi, or Xi, the damping factor, the overall damping factor, is always larger than 1, which means that the system is over critically or underdamped.
Over.
Over. So the series of two non-interacting first-order systems gives rise to a second-order over-damped system, because the arithmetic average between tau 1 and tau 2, the arithmetic average between the two numbers, always exceeds the geometric average. What if tau 1 is equal to tau 2? What if two systems in series have the same time constant? Simply, Xi, the damping factor, will be, in this limiting case, equal to 1. And so the overall system will be critically damped. And so critically damped systems are a particular case of over-damped systems. So guys, are you still there? Is that clear?
Yes.
Yes.
Okay.
Quick
Now-
question.
Yes, please.
Is the order of the system determined by the number in series, or is it always second order?
No. Good question. Good question. So if you have two first-order systems in series, the overall system will be second order. But if you have three first-order systems in series and you multiply the transfer functions one by one, the order will be 3. So if you have four first-order systems in series, the overall system will be fourth order. So this specific example that I mentioned applies when you have two first-order systems non-interacting in series. Does this make sense for you?
Yes, thank you.
Mm-hmm. So as a limiting case, guys, think about a distillation column. You have 100 trays in series. So would you expect the distillation column to be a first-order system or an extremely high-order system? That's right. That's right. And very soon we will see the dramatic implications of this. Now, I know what you are waiting for. I know that all of you is anxious to answer this question. So, how second-order systems respond to disturbances? Really, guys, don't be afraid, because the music is always the same. The procedure is always the same. It's very repetitive. And let's see. We have a second order system, overdamped. We are talking now about overdamped systems. At the time equal to 0, an impulse disturbance of amplitude A hits the input. How the output responds? What is the effect on the output? Again, the response in the Laplace domain, follow my pointer, is equal to the transfer function times the Laplace transform of the disturbance. So the Laplace transform of the disturbance is A, because we have an impulse of amplitude A. And if you go to the table, the Laplace transform of the impulse of amplitude A is A itself. The transfer function G is the generic transfer function of a second order system with xi larger than 1. And so the overall response in the Laplace domain is the one that I'm highlighting in the Laplace domain. Kpa divided tau square s square plus 2 psi tau s plus 1. Make sense? Should I repeat?
That makes sense.
Okay. Again, this does not answer the question. We have to anti-transform back to the time domain. How can I do this? Now you have to invent a method to anti-transform. So you can use the partial fractioning method, if you like it. You can use the Heaviside method, if you like it. So obviously, psi is positive, is larger than 1. We have real and distinct poles. So here you have to expect to apply the first Heaviside theorem. And I will leave to you doing this. We are not interested in the mathematics. We are interested in the physics. So the response will be the one that is highlighted there in the red rectangle. I know that this expression looks very unpleasant, but it is what it is. So we are not interested in equations. We are interested in understanding the physical meaning. So let's build up the graph of this response. If the time is equal to 0, what happens there? We have the difference of two exponentials. Each of them goes to 1 when time goes to 0. So their difference goes to 0. And so at the time 0, the response is 0. Make sense?
Yes.
What if time goes to infinity? Well, both the exponential terms will go to 0. Just they will decay to 0. And so basically the response will be a curve that qualitatively is the one that you can see here, is a red curve. So let me explain this a little bit better. So let's report F, the input or the disturbance, and Y, the response. So the disturbance is a unit impulse, an impulse of amplitude A. The response will be something like that I'm highlighting now on the screen. So what is the first thought you have if you look to this response? That is really sluggish. Basically, the response of the system starts to increase, reaches a maximum, and then it goes to 0. Because the impulse is not a permanent disturbance, it's a temporary disturbance. So the system is self-regulating. The system goes back spontaneously to the original steady state. Does this make sense?
Yes.
Now, guys, what I want you to do is compare the response to the same disturbance of a second order overdamped system and a first order system. What is the first thought you have? Please look at them and tell me what is the first thought.
It's less of a change at the beginning.
I don't know if I'm interpreting correctly. Just let me know if I'm wrong. Do you mean that the second order system is more sluggish?
Well, it's more sluggish, but also there's not that sudden shock of it changing.
Yeah,
it's a
I
gradual
see.
change.
I see. That's true. For sure, there is a more gradual change, but the dramatic effect is that the response of a first order system is relaxed much faster. The response of a second order system is relaxed in a very sluggish way, which means that the effect of the disturbance on the output will persist much longer. Make sense?
Yes.
And is this good or is bad? Absolutely bad. Absolutely bad. When you have a disturbance, you want the effects of the disturbance to disappear as soon as possible. You don't want the response to be, relaxed over long times, because this may put you in an unsafe situations. So, first conclusion, second order systems are slow. They are sluggish, much more sluggish than first order systems. And be aware, guys, that the higher the order and the more sluggish the response of the system will be to a given disturbance in the input. That's why higher order systems are not easy to deal with. Second situation, second scenario, step change of amplitude A in the input. How will the second order, overdamped second order system will respond? Simply multiply the transfer function by the Laplace transform of the step, A over S, and you get the response in the Laplace domain. But you want the response in the time domain. So you have to anti-transform using what? Heaviside partial fractioning methods, as you wish, is up to you. So the anti-transformed is this unpleasant expression with two exponentials. But we are not interested really in the mathematics. We are interested in the physics. So if you have a step disturbance in the input, the output will respond like this. You will get a sigmoidal response. The asymptotic response will be kPa, which is the limit value of this function when time goes to infinity. Simply, when time goes to infinity, the two exponentials will go to zero, and so the response will go to kPa. Again, let me show you this in a different way. So the response will be a sigmoidal curve. Do you remember the response of a first order system? It was basically much faster. Do you remember it? It was something like this. Let me draw. Let me just draw. Do you remember it?
Yes.
So, is the response of the second order system overdamped to a step faster or slower?
Slower.
Much slower. The system is sluggish. As you can see here, there is a dead time. There is a certain time that you have to wait before you observe any response in the system, which means that the response will arrive a little bit later than the disturbance. Obviously, the step is a permanent disturbance, and the system will evolve to a new steady state, obviously, which will be kPa. Now, second observation, if the damping factor increases, so the damping factor is larger than 1 because the system is overdamped. So let's say it is 2. If the damping factor increases from 2 to 3, 4, 500, 1,000, million, basically the response of the system, and you can verify this with the calculation becomes even more sluggish. So the higher psi, the higher the damping factor, and the more sluggish the response will be. Does this make sense?
Yes.
So if you have a overdamped system, you know, the best scenario is psi little bit larger than 1, but not 3, 10, 100, 1,000, because a very high value of psi will make the system extremely, extremely slow, which is bad. So please, in this slide 27, you can compare F, the disturbance, which hits the system at the time 0, and then the response of a second order overdamped system and the response of a first order system. See how different they are. Basically, they are similar asymptotically, but at short times, the second order system is much slower than the first order system. And the third order, the fourth order, the 10th order system is even more sluggish. So you don't want to have to do with sluggish systems, because the effect of the disturbance will arrive later and will persist much longer. Okay, does everything make sense for you guys?
Yes.
Yes.
Okay, so before we close, before we close, the results of the homework were posted and they are extremely positive. So please, let's go ahead like this. And again, they match perfectly, the average matches perfectly with what I saw in previous years. We are a little bit short with the time. We have the middle term soon. So I will solve the homework and I will post a separate video with the solution. Even though the solution is available on Canvas, I will play a separate video where I will show you the solutions live, let's say, and I will highlight the most common mistakes. Just for you to know, the response to the theoretical questions was much, much, much more successful than last time, as expected. But there is still a 50% of the class that didn't provide the definition of the Laplace transform, so didn't answer the question. And so I will go through that in a separate video that will be probably posted this afternoon or so. It will be a short video with the solution. However, the analytical solution is already available on Canvas in PDF form for you to download. Anyways, the results are extremely positive. Please, let's go ahead in this way. I will talk to you in a couple of days. Stay safe. Bye-bye.
Thank you.
Thank you.